Hey guys, I want to take a few moments here to talk to you about stoichiometry and how it changes things from the conversions that we've been doing. Now, it's not going to be a big step up, but it is a little bit more work than just doing the simple mole conversions. So I want you to do your best to try to take notes that you can use for practice problems later while you watch this video. Let's take a moment to think about what we have done so far. Well, so far we've done mole conversions that have involved things like atoms, molecules, formula units, etc., moles, and grams. So you guys hopefully can remember that when you're converting between atoms and moles, you are going to use Avogadro's number, because what Avogadro's number is that 1 mole of any substance is equal to Avogadro's number when you're talking about particles, so like atoms, molecules, formula units, etc. You also should hopefully remember that the number of grams in 1 mole of any substance is known as its molar mass or formula mass. Which means that 1 mole of any substance is equal to the number of grams that you get from the periodic table, whether you have to add them together or just read straight from the box. So all of the conversions that we've done so far have been moles to grams, grams to moles, so those are both using the periodic table, moles to atoms and atoms to moles, which is using Avogadro's number, and then grams to atoms and atoms to grams, which have been the two-step problems which involved both conversion factors. So the way things are going to be changing in this unit is that we're not just going to be converting between units of the same substance. We'll be using chemical equations to convert between different substances that are involved in the reaction. So if you look at this picture here, it's not just one thing that I'm converting between. Like, I'm not just going between mass of a compound, in this case compound A, to moles of it, to particles of it. It's not just that anymore. Now we can go something from mass of compound A to maybe mass of compound B. The way that we use this image is by considering it like a road map. So you have hopefully somewhere in your notes the road map that we did when we first talked about moles, and if not, it was on the previous slide. But now the only thing that is changing is that when we're talking about two different substances, it's like we're going to fuse two mole maps, and the only connection, also known as the only new thing in this unit, is going to be what happens right at this arrow. And I don't want you to fret. All of the conversions that we have done so far are still going to be applying. As long as we're talking about one substance, you'll do everything the same way that you've done before. The only thing that's going to change is that it might take you an extra step to get to just one roadmap. So because we're using balanced chemical equations to describe reactions that we see, we are now able to use information about what's in the reaction, so the reactants and the products, to learn about the other substances involved in the reaction. Now, what this means is that I can tell you something about water, and you could return tell me something about hydrogen or oxygen just by using the chemical equation. And that's because the coefficients describe the number of substances that interact as the equation is written. So when you look at water, so H2O decomposing into hydrogen and oxygen gases, the only way that that would work as that's written is if you have two water atoms, or molecules, that both decompose, and you'll have two sets of H2 molecules and one O2 molecule. So anytime that water decomposes, it will always be two of them together decomposing to form two sets of hydrogen molecules and one oxygen molecule. This is why we balance the equation. So when we compare the coefficients of one substance to another in the same equation, that is known as determining the mole ratio. So when I say that for every 2 waters that you have decomposing, you'll come up with 2 molecules of H2. So the mole ratio of the water to hydrogen would be 2 to 2, which happen to be the coefficients. So what's new now is that we can now perform calculations including moles of water to moles of oxygen or hydrogen. So now we're not just going between moles and grams and atoms of one substance. We're going to hop on over to one of the products and see what goes on. We can also convert now between molecules of H2O and molecules of O2, or grams of H2O to grams of O2. So it's no longer, again, just going between one substance. It's about using the balanced equation to convert between substances that are involved. All you need is the mole ratio to convert between substances. And the only thing that you need to be able to determine the mole ratio is just by balancing your equation, if it's not already balanced for you. So what this all means then, and I pulled back the graphic from the combined mole map because the mole ratio is the only thing that you can use to convert between substances. So like if you look at this roadmap, you'll see that there's no arrow to go from mass of compound A to mass of B. So you can't go from grams to grams directly. It is actually a 3-step process. So you would need to go from mass of A to moles of A to moles of B to mass of B in order to determine the number of grams that would react. Now, this might be a little bit confusing, so keep this mole map handy. As long as you can understand what's happening along each arrow as you convert between units, everything will be dandy. And remember that this arrow, what happens here is the mole ratio. So it's where you might say 2 moles of A reacts with 2 moles of B or something. I want to finish up this introductory video by doing an example with you. So I have shortened or truncated the mole map a little bit here because we're not going to be dealing with molecules or atoms. So what this question is asking is that if 53.0 grams of water decomposes, how many grams of oxygen will be released? Now, this is the same equation that we've been talking about this whole time. So if I have 53 grams of water, I'm starting somewhere up here on my mole map. So I'm going to start with the number and unit I'm given. Now, I know by looking at my mole map, my goal, which would be mass of oxygen, which is another substance, so we can't just do a direct conversion. I first have to go to moles of my first compound. So for every 1 mole of water, now I'm going to use the molar mass, which is 18.02 grams of H2O. Excuse me. So now grams cancels, and I'll be in moles of water. So now I'm here. Well, I got to go to moles of B next. Remember, here was the mole ratio. So if you think about this equation, you know that for every 2 moles of water that reacts, you will get 1 mole of O2. What that means is that I'm going to write that as a fraction. So 2 moles of H2O, I just pulled that from the balanced equation, and 1 mole of O2. Again, right from the balanced equation. And the reason I wrote it in this order instead of 2 over 1 is because I need moles of water to cancel out, and I'm eventually trying to get my answer in grams of oxygen. Well, I don't want my answer to be moles of water and try to get that to moles of oxygen. I need the moles of water to cancel out and moles of oxygen to be left untouched at this moment. So now we're here, and we need to get to here. Well, the thing that we do now is go back to the periodic table, look at the molar mass of oxygen. However, don't get tricked. This molecule is not just 1 oxygen, it is 2 together. So for every 1 mole of O2, you actually have 32 grams of O2 because 1 oxygen plus another oxygen is 16 plus 16. So be careful about that. So if we plug that into our calculator and round to sig figs, we would get an answer of 47.1 grams of O2. So what we've done now is, starting up here in the top left, we've followed along the road map to get to the top right. And again, we had to go through all those steps because there is no direct conversion here. There's no arrow between the orange boxes.